I'm just going to run through the derivation of the formula for the period of a mass spring system. So I'm going to start here with Newton's second law. And we're going to do it in differential form. So if you've got a mass spring system, the force is spring force, which is equal to minus kx, and acceleration is the second derivative of position with respect to time. So here we have a situation where the second derivative is equal to negative the variable times a constant. K and m are going to be constants for a given system. So then for what kind of function does this hold true? Well, it's only for a sine or cosine function. So x has to be some kind of cosine function. Well, we'll use a cosine function. So again, this is a general cosine function. So then the second derivative of that, we chain rule out two omegas. Cosine becomes negative sine and then becomes negative cosine. So, and we did this a couple days ago. This would then be the formula for acceleration. By comparison, if we look at these two, then the position times what? Well, there's an a. The difference, we've got a negative omega squared. So negative omega squared x is equal to acceleration. That's the pattern we see in simple harmonic systems. Here we see something times x equals d squared x by dt squared. So what does that mean? Negative k over m equals negative omega squared. So omega equals square root of k over m. And therefore, period is 2 pi over omega. So that's 2 pi over root k over m, which causes this fraction to flip, which gives us 2 pi root m over k. The AP test is fond of having you write this equation, or maybe it's the answer to a multiple choice question, but of having you write the differential equation for a simple harmonic system. So that's what it is. Right? For a pendulum, it also winds up being simple harmonic, but it's a little bit different. So we consider a pendulum, say it's displaced an angle theta from the horizontal at a given point. So then, what force is acting on this? Gravitational force is acting on this. The acceleration is changing directions. It's not 1D. Over here, the acceleration was one-dimensional. But we can say that this is one-dimensional if we consider angular stuff. So if we say net torque equals I alpha, then we can deal with this system pretty easily. So the net torque, well, we've got is caused by gravity. There's also a tension, but that causes no torque because our pivot point's right here. It points straight toward the pivot. So we've got mg, and that's acting at an angle of theta to the lever arm. So this angle is theta. Therefore, the net torque is mg sine theta. And whatever direction the angular displacement is, the torque is acting in the opposite direction. So the angular displacement is this way, counterclockwise, sorry. Then the torque is going to be back clockwise, so it's negative mg sine theta. And that's equal to I alpha. Well, this is for a simple pendulum, this is a point mass. So our I is mr squared, and the radius is just the length of our string, which we call L. And alpha is the angular acceleration is the second time derivative of angular position. So now we notice mass cancels out. Which when we do or did, depending on when you're watching this, our investigation, you'll notice that mass doesn't have an effect on the period of a simple pendulum. And then here's where we run into a wrinkle, because this is a sine theta. So this is almost like the pattern here. We've got a constant times something equals its second derivative. but we don't just have the variable, we have the sign of the variable. So what do we do with that? Oh, I'm dumb. Sorry. Net torque is R cross F. I forgot my R over here, so we need to multiply this by a factor of L. Just looking at this and realizing I was going to get the wrong answer. So we've got L times mg sine theta. So then one factor of L also cancels. Okay, now I move this over, minus g over L sine theta equals d squared theta dt squared. Now this isn't quite that simple harmonic pattern that we saw with the mass spring, but if theta is small, and generally we use about less than 15 degrees. Your textbook might say 10. I don't know. There isn't like an official cutoff for when small angle approximation stops holding, but you guys may know, especially those of you who are doing BC, you've done the Taylor series for sine. But when theta is close to 0, sine theta is about equal to just theta. So first off, the first thing to note here, oops, I missed my equal sign. First thing to note is that a simple pendulum is only simple harmonic for small amplitude oscillations. Okay, if you pull this pendulum, if you pull this mass up to the horizontal, now the swinging system isn't going to be simple harmonic anymore. So we can't use the equation that I'm about to derive. Okay. Following the same pattern as before, this is, if we write out all the equations, minus omega squared theta equals alpha. So for a pendulum, we get that the angular frequency is equal to square root of g over L, and therefore the period is equal to 2 pi root L over g. Now, be careful here, angular frequency is like angular velocity for uniform circular motion, but it is not the same thing. So the angular frequency of this pendulum is not the same thing as the angular velocity of this mass. So the angular frequency, omega, is a constant for the system. It's equal to 2 pi over the period. But that is different than the angular velocity. If we write our equation for a pendulum, our theta angular position as a function of time is equal to the amplitude, which is the maximum value of theta, cosine omega t plus phi, where omega is the angular frequency. If we then take a derivative of that, the angular velocity is equal to negative theta max omega cosine omega t plus phi. And now we've got a weird situation where this omega represents the angular velocity at any given time for the mass swinging back and forth, and these omegas over here represent the angular frequency that is equal to 2 pi over period. So you have to be careful. Most times for a pendulum, use this equation, but don't actually get into using the angular velocity and angular acceleration equations. You can, but it winds up being kind of weird. So you have to watch out for that. But again, just like for the mass spring on the AP exam, they might ask you to generate this equation or something like it. So you need to this is a case where you need to not only know the result, but you should know the derivation of where these formulas come from for both the pendulum and the mass spring system.